Okay, Chemistry 101. Here we are in section 6.8, which deals with mechanisms and arrow pushing. And you've seen the use of curved arrows before in this class. We use them to show how electrons move when bonds are being broken and bonds are being formed. So we use them in chapter 3 when we looked at acid-base reactions. For example, here's a base and it is reacting with an acid, which is a proton donor. But this curved arrow here, that represents a bond being formed. So this is a bond that is being formed. And the second curved arrow that you can see here represents the flow of electrons that represents a bond being broken. So this one here represents a bond being broken. So we have the formation of a bond and a bond being broken simultaneously in this acid-base reaction. Well, there are four main ways that electrons move in polar reactions that you have to be aware of. Okay, we have a nucleophilic attack. We use Na as an acronym for that. Loss of a leaving group, for which we use LLG, a proton transfer, PT, and a rearrangement, which we call RGT. That's the acronym we use to represent rearrangement. So let's get in it, and we'll start with a nucleophilic attack. Now that we've determined what a nucleophile and an electrophile are, let's say we have bromide, which can act as a nucleophile. It's got a negative charge. It's got a pair of electrons to donate. And we saw that a carbocation makes a good electrophile. Well, we can draw a curved arrow that shows a pair of electrons from the bromide attacking the electrophilic center or the carbocation, right? Because there's an empty p orbital here. So we draw this curved arrow, and that represents a bond being formed between the bromine and the carbon. That's this bond right here. So the tail end of the arrow, right? The tail end down here starts on the electrons where the negative charge is. The head of the arrow ends up on the nucleus, right? Because it's a nucleophile, it's a nucleus lover. And the electrons end up being shared. Those electrons are shared in this new bond. So new bond that we formed in the nucleophilic attack. A nucleophilic attack can require more than one curved arrow. If you take a look at what's happening here, we have our alcohol, which can behave as a nucleophile. It's got a pair of electrons here. And the reason why this can behave as an electrophile is because if you think of this carbon here, it's got a dipole not only going towards the oxygen, but another one going towards the chlorine. So you bet that it is going to be delta plus. Well, if that carbon is delta plus, that's great. And if I was to just draw this curved arrow showing the nucleophilic attack like this, the problem is that I would have 5 bonds to my carbon, wouldn't I? I'd have 1, 2, 3, 4, 5, and that is too many bonds. And so I have to break the pi bond and show the electron density going up onto the oxygen like that. So we drew 2 arrows simultaneously. There is another way you could think about this, because the electrophile that they've drawn here actually has a resonance structure like this, and you guys all know how to draw this resonance structure. Since we have a pi bond right here, we can draw this resonance contributor where we have a positive charge on the carbon and a negative charge on the oxygen. So we can clearly see that this is an electrophile. So that's another way that we could draw it. However, this structure is going to contribute more to the overall resonance hybrid. And so that's why we wouldn't just draw this and draw a nucleophilic attack to it. So that's why we have the 2 arrows occurring simultaneously here on our nucleophilic attack. As I told you earlier on, a pi bond can also behave as a nucleophile. Now here's an example that's going to come up much later. This is an aromatic ring, a benzene ring, acting as a nucleophile to sulfur trioxide. That's SO3, sulfur trioxide, which is a gas. Anyhow, you see that the pi bonds, and you see that the tail of the arrow doesn't start right on the pi bond here, but you could actually start it on the pi bond like that. But you see that you have the nucleophilic attack, and then you're not going to have more bonds to sulfur, so they have the second curved arrow drawn here simultaneously. Now, although we're not going to look at this until organic chemistry 2, we will see many examples of pi bonds behaving as nucleophiles in organic chemistry 1. Notice that only one of the carbons that's involved in this pi bond is actually using the pair of electrons, okay? Because the other carbon is ending up being a carbocation. It's ending up electron deficient. So that's a nucleophilic attack. The next one was the loss of a leaving group. Now, if you're like, what's a leaving group, Mr. Dion? We're going to talk more about what a leaving group is later, but I can tell you really quickly what a leaving group is. It's going to be the conjugate base of a strong acid. Okay, what are the strong acids? Things like HBr, HCl, HI, sulfuric acid, perchloric acid, nitric acid, hydronium. Those are strong acids. Basically anything with a pKa less than 0, with a negative pKa. So here we have, this is called tert-butyl bromide. You see that the leaving group is leaving and the bromide is the leaving group. Why is it leaving? Because remember, bromide is the conjugate base of HBr, which is a strong acid. Now here we're only showing one bond being broken in order to show the loss of the leaving group, and we form the carbocation and the bromide. However, it's very common to have more than one curved arrow required to show the loss of the leaving group. Now, this is an intermediate. It's called a Meisenheimer complex. It results from what's called an SNAR reaction, which isn't covered in Organic Chemistry 1, but the curved arrows still stand. I would still expect you to understand these curved arrows. You see that there's a flow of electrons going all the way from the negative charge on this oxygen all the way down here in order to cause the leaving group to leave. Why would chloride leave, right? We're going to lose chloride here, Cl minus. Chloride is the conjugate base of HCl, which is a strong acid. So that's the loss of a leaving group, which can require one or more arrows depending on the situation. Probably the curved arrow that shows up the most in this class, I think if you had to actually tally them all up, which I've never done, would be the proton transfer, right? This is the one we call the PT, proton transfer. And we saw proton transfers back in the acid-base chapter, in chapter 3. A proton transfer requires two curved arrows. Here's the proton transfer occurring between a hydronium ion and the oxygen of a carbonyl. You see that the lone pair on the carbonyl is acting as an electron donor, and the acid is acting as an electron acceptor, okay? And we're ending up with a protonated carbonyl over here. That's a proton transfer. Now, the deprotonation of a compound is sometimes shown with a single arrow, like using a minus H plus, like is shown here. I will never use that in this class. That is a shorthand. I wouldn't recommend trying to use shorthands for anything in Organic Chemistry 1, unless it's something that I really told you, go ahead and take the quick way out. But what it's saying here is that, let's say you wanted to represent this proton transfer here, the removal of this proton or the transfer of that proton to water. If you saw two organic chemists, just jamming on a chalkboard or something, they might write something like this, where they just write this one curved arrow, and then they write minus H plus. Again, it's a shorthand. I wouldn't recommend using it in this class. In fact, in my notes, I see a big, in bold letters, I wrote, "Don't do this yet!" exclamation point. Anyhow, something you might want to use later on once you're more confident. But with proton transfers, sometimes we have to use multiple arrows to show the complete flow of electrons when we exchange a proton. For example, let's say you have this ketone here. Well, you could just draw a curved arrow to show the proton transfer and then the formation of a carbanion like this. However, if you look at these two resonance contributors to the overall resonance hybrid, you can see that this one is going to contribute more to the resonance hybrid because the negative charge is on the oxygen, right? This is going back to the rules that we learned in chapter 2. So that is why it would be probably more accurate to draw 3 curved arrows here, which results in the formation of this here. All right. So this kind of counts like a proton transfer with resonance all together, combined in a beautiful proton transfer sandwich, if you will. All right. The next one is a rearrangement. So this is the last one. So we had the nucleophilic attack, the proton transfer, loss of leaving group, and now the rearrangement, for which we use the acronym RGT. Okay. So you guys remember carbocations? Of course you do. We talked about carbocations quite a bit in this class, and we said, well, a tertiary carbocation is more stable, right? More stable than a secondary, which is more stable than a primary, which is more stable than a methyl. What happens is the reason why the tertiary is more stable than a secondary, so on and so forth, is that carbocations are stabilized by neighboring groups through slight orbital overlapping that we call hyperconjugation. Oh, maybe I didn't talk about carbocation stability. Sorry, I might be getting ahead of myself. But the bottom line is this. If you have a carbocation, this, you see here we have protons, and here we have a methyl, which counts as an R group. The more R groups that you have surrounding your carbocation, the more stable it is. Now, the reason why is based off of something called hyperconjugation. I'm never going to ask you to write me an essay about hyperconjugation, but the bottom line is that when you have an R group, and this is the methyl group here that I have in this yellow circle, the bonds, like this bond here, is formed between an sp3 hybrid orbital and the 1s orbital of the hydrogen. Well, there's two electrons in this orbital, and they can kind of overlap with the p orbital, and they kind of dump some electron density in there, and it stabilizes it. So in a nutshell, and this is where I was getting ahead of myself, is that the hyperconjugation, which comes from R groups, explains the carbocation stability trend that we see here. We see that a tertiary carbocation, which we can just label like this, is more stable than a secondary, which is more stable than a primary, which is more stable than a methyl. So the bottom line, again, I'm repeating myself, the more R groups we have, whether they're, and it doesn't matter if the R group is a methyl, ethyl, propyl, isopropyl, whatever. The more R groups you have surrounding your carbocation, the more hyperconjugation you have, and the greater the stability of the carbocation. So I'm definitely going to ask you a question about this on your quiz, something about carbocation stability, and probably something about hyperconjugation. So this is something that you need to be aware of, hyperconjugation. And again, it's just the donation of electron density from bonds in the R group into the unhybridized p orbital, which serves to stabilize that p orbital. In terms of rearrangements, okay, first we had to look at carbocations, and we had to talk about the stability of carbocations. Well, the reason that rearrangements are going to occur is in order to produce a more stable carbocation. So it's imperative that we know this trend here, right? A secondary would rearrange to form a tertiary. A primary would rearrange to form a tertiary or a secondary, so on and so forth. Well, how are they going to rearrange? There's two types of rearrangements that you have to be concerned with in Organic Chemistry 1. The 1,2 hydride shift and the 1,2 methyl shift, which is sometimes called the 1,2 methide shift, but that's nothing to really worry about. If we look at this carbocation right here, you notice that there's a hydrogen next door to it. Well, if that hydrogen was to take its pair of electrons and move over here, was to shift over here, we go from, in this case, having a secondary carbocation to having a tertiary carbocation. A tertiary is more stable than a secondary. Therefore, this hydride shift will occur. We can also have what's called a methyl shift, okay, which is exactly what it sounds like. It's the shift of a methyl. Here we have that secondary carbocation again. If you look next door over here, there's a methyl group. If that methyl group were to move over, we end up with a tertiary carbocation, which again is more stable. So shifts, two things about these shifts. Number one, they can only occur from the next door neighbor. Okay, you can't just pull any old methyl group off the molecule. It's got to be on an adjacent carbon. And the shift is only going to happen if a more stable carbocation results, right? The reason that both of these happen is because we're going from a secondary to a tertiary carbocation. Well, how would I put all of these together? Right? How do I put all of these, different patterns of arrow pushing together? The nucleophilic attack, the loss of leaving group, the proton transfer, the rearrangement. Well, I think the first thing you want to do is to be able to identify these types of arrow pushing patterns. Because when we look at a multi-step reaction mechanism, which is kind of where we're headed in this class, it's always going to be a combination, some combination of these four patterns. For example, here we start out with a proton transfer. You can see that the hydroxyl is being protonated by HBr. Then we have a loss of a leaving group right here. Right, we see we're losing water. Why would you lose water? Because water is the conjugate base of hydronium, which is a strong acid. It has a pK of minus 1.7. Then we have a carbocation rearrangement. Why is there a methyl shift occurring here, right? This is the methyl shift, or the 1,2 methyl shift, either way. Why is this occurring? Because here we have a secondary carbocation, and now we've formed a tertiary carbocation. And then lastly, you see that we have a nucleophilic attack, right? Bromide is acting as a nucleophile. We have a carbocation, which acts as an electrophile, and there you go. We're also going to see many, many cases where two of the patterns can occur at the same time. Here you have a nucleophilic attack, right? The hydroxyl is acting as a nucleophile. You know that there's a dipole here, so the carbon is electrophilic, okay? Well, not only do we have the nucleophilic attack occurring on that delta plus carbon, but you can't have 5 bonds to carbon, and so our leaving group is going to leave at the same time. So this is our loss of leaving group. Why would chloride leave? Because chloride is the conjugate base of HCl, which is a strong acid. Remember, leaving group, this is one I talked about quite a bit. The loss of leaving group, a leaving group is the conjugate base of a strong acid. Okay, well, that was a lot of information. Let's see if we can apply that information and describe what's going on in these 3 steps. So I'm going to call the first step A. I'm going to call the second step B. And I'll call the second step, you guessed it, C. Could anybody identify what's going on in the first step? Would this be a nucleophilic attack? Proton transfer? Yeah, that's what it looks like to me. I would say that you are right, Autumn. This is a proton transfer, right? Because you see that we're transferring this proton from the ester, okay, and it's being transferred to the hydroxyl, right? And we're drawing 2 curved arrows at once, right? Both of these are part of the proton transfer. What about the second one? Could anybody describe what's happening in the second one? What do you think's happening in the second one? We have a carbanion, which could, yes, exactly. Thanks, Kelly. We have the carbanion, which can be a good nucleophile. We have a dipole going this way and this way. We have a delta plus here, so this is our electrophile. Okay, so what's happening here is a nucleophilic attack. Absolutely, this is a nucleophilic attack. We have a nucleophile and an electrophile. And then what's happening in C? We're losing an alkoxide here. Yeah, absolutely, Mackenzie. This is a loss of leaving group. I just want to address one quick thing. If somebody's really quick, and I know you're all very good students, you know, if you're saying, hold on, Mr. Dion, loss of an alkoxide, the conjugate acid of an alkoxide is an alcohol. That's not a strong acid. That's not, how can that be a leaving group? The answer is it depends on the situation. Okay. So we'll talk more about leaving groups later on, and you know, what's a good leaving group and what's a bad leaving group and all that kind of stuff. But for now, all we wanted to do was to identify these types of mechanisms, the 4 types of mechanisms that we've looked at. Well, as you can imagine, when it comes to drawing curved arrows and reaction mechanisms, that there are some rules that we have to abide by in organic chemistry, right? There's always some rules involved. I want to go over the rules with you, and the rules, I can cover them with you in class, of course, like I always do. I try to cover everything in my classes, but it would be worth, you know, going over the rules again when you're practicing, or maybe keeping them keeping that part of your textbook open while you're practicing, just to make sure that you don't violate any of the rules, because you don't want to violate any of the rules. So first one is that a curved arrow is always going to start on a pair of electrons. Okay, it's either going to start on a pair that's in a bond, or it's going to start on a lone pair. So a lone pair is pretty easy to draw that. You just make sure the tail of the arrow starts right on the lone pair. When it starts on a pair of electrons in a bond, it's good to start the tail of the arrow right in the middle of the bond. So here's, if this is the bond, this is kind of the middle here. So make sure the tail starts on the middle. If it starts on a nucleus, right, that's going to be a bad thing. So you don't want to be doing that. Anyhow, if you look at what's shown here, right, don't draw this. Okay, this is totally screwy. There's nothing wrong with this curved arrow, right, because it's starting on a pair of electrons. So the first one is cool. This is, we'll give that the old yay sign. Okay, we'll give it a check mark. Looks good. But the second one is no good because it's not starting on a pair of electrons. It's actually starting on an atom. Okay, it's not starting on a lone pair. It's not starting on a bond. So we'll put here bad arrow. All right. Never place the tail of a curved arrow on a positive charge. So if you ever do that, you're making a big boo-boo. Okay, like something crazy, that I would never want to see any of you guys draw would be something like this. There's no such thing because there's no electrons here, right? That's got a positive charge. So that's impossible. So do not write that down. We'll cover that with a big old X. Okay, impossible, as we say in French. The arrow is going to end on a nucleus. Okay. So the arrow is either going to end on a nucleus or it's going to end between two nuclei. Okay. So here the arrow is, forming a bond because it's between this nucleus and this nucleus. Whereas here, this pair of electrons from the bond is just ending up on the chloride. So it's ending up being a lone pair. Whereas here, again, this arrow results in the formation of a bond, which is, whatever bond, this one, let's say. Okay, so bond, we'll put here bond formed, like that. Another rule is, and I think that most students would figure this one out on their own, so we don't break the octet rule, okay? We never draw more than, we make sure that carbon, nitrogen, oxygen, and fluorine could never have more than 8 valence electrons. Right, that's why there's a big problem with this curved arrow on the bottom left. Huge problem here, because if this represents a bond being formed, well, then you've got 5 bonds to a carbon, which is a big no-no in organic chemistry. So here you'd have to have the nucleophilic attack, and you'd have to have the loss of leaving group occurring simultaneously. Otherwise, you're in violation of the octet rule. What else? Let's see here. Where am I? Any curved arrow drawn should describe one of the 4 patterns. Okay, so if you try to draw something that doesn't fall under the nucleophilic attack, so what are our 4 patterns? You got nucleophilic attack, you got loss of leaving group, you got proton transfer, and you got RGT, the rearrangement. It's got to fall under the umbrella of one of those, or you're in trouble. You've done something wrong. I mean, the thing is, this one here, it says this arrow is unreasonable, which is totally true. I mean, it violates the octet rule, right? You've got too many bonds to this carbon, which already has 4 bonds, and it doesn't match any of the patterns that we've seen. So, not only do you have to be able to draw proper arrows, but you got to be able to recognize arrows that are incorrect too. But again, and you know what I'm going to say, the best way to master it is to practice it. So let's start with a problem. 6.15 comes right out of our textbook. And, for these kind of questions when you're starting out, and you don't have to do this all the time, but I like to, when I'm, introducing the subject to my students, we like to include every lone pair. So I like to start by drawing in all my lone pairs. Obviously, by the time you're at the end of Organic Chemistry 2, you probably don't need to draw every lone pair. It's not imperative, but it comes in handy in Organic Chemistry 1. All right. If anybody drew the curved arrow, because it's really tough for me to ask, show me the curved arrow, you guys, over Microsoft Teams. But could anybody tell me what's happening here? Would it be a proton transfer, a loss of leaving group, a nucleophilic attack, or a carbocation rearrangement. Can anybody tell me which one of these patterns would be demonstrated here? Because I'm sure that somebody drew the curved arrow or tried it. Anybody able to? Yeah, it's a nucleophilic attack. That's right. Right, we have the carbocation, which makes a great electrophile. Okay, and we said we got lone pairs on our oxygen here, so this is a very good nucleophile. Okay, and I mean, if you've got a carbocation, that's super starved for electrons, and so what's going to happen is your nucleophile is going to attack the electrophile. Now, the curved arrow, you could draw it as long as you start the tail here. I mean, you can draw it this. That doesn't matter. You can draw it like that. That doesn't matter. I like to just try to draw them as clean as I can, okay? And like I told you in the acid-base thing, you could technically draw it like this, okay? I wouldn't grade that correct. It's kind of ridiculous, but the idea stands, okay? The pathway is not important. It's important that the tail of your arrow starts on the pair of electrons and the tip of your arrow starts on the electrophilic center. There you go. So a nucleophilic attack. Got a little bit of practice drawing some curved arrows. I want to talk to you a little bit more about carbocation rearrangements. Okay, whenever you see a carbocation in an organic chemistry, and they come up all the time, you're at a crossroads, right? You're at a fork in the road whenever you see this. You got to ask yourself, is this going to undergo rearrangement? Is it going to undergo a 1,2 hydride shift or a 1,2 methyl shift? Is there something that could happen that would produce a more stable carbocation, right? This is a secondary carbocation. Okay, this is secondary. You know, would this rearrange? Could anybody answer that based off of what we saw about rearrangements earlier? The hydride shift and the methyl shift? Could anybody answer that? Okay. So we have to ask ourselves, will this rearrange to produce a more stable carbocation? All right. So the only possibilities for rearrangement are for something to rearrange from here or something to rearrange from here. So will it rearrange from one of those sides? Well, on the carbon that I have circled in red, the only thing that there are on that's on that carbon, I should use the red pen, are hydrogens, right? If a hydride shift was to occur, right, what would you end up with? You'd end up with this. Let's draw it. You'd end up with this in a positive charge here. You would go from a secondary carbocation to a secondary carbocation. That is not going to happen, okay? Because you don't increase the stability whatsoever. No improvement in stability, so it's not going to happen. So I see, you know, somebody says, okay, well, maybe a methyl shift. Okay, well, if I look at this methyl group over here, okay, there's a methyl group here. If I was to shift that methyl group over here onto this carbon, then I'd end up with this. So I'd end up with this, like that. So I'd put the methyl group over here, but then I'd still have my positive charge here. So I'd go from secondary to secondary. So that's not going to occur either, right? I'm not increasing the stability. So let's erase this. And let's consider what would happen if you were to shift the hydrogen, right? Because there is a hydrogen here. If this hydrogen was to shift over here as a hydride, right, what would you end up with then? Let's draw the carbon skeleton. You'd end up with this. Then you'd have the carbocation over here. So you'd go from a secondary to a tertiary carbocation. And so this rearrangement is going to happen, okay? You're going to get that 1,2 hydride shift in this case, which again, sometimes we just call a hydride shift. All right, so in this case, it would undergo rearrangement. It would undergo a 1,2 hydride shift in order to produce a tertiary carbocation, which is more stable than a secondary carbocation. Give me a thumbs up if you follow me on that one. Just evaluation of the carbocation in determining whether rearrangement is going to occur or not. Or if you have a question, feel free to stop me. All right. Okay, well, let's take a look at some more information about carbocation rearrangements. If you're wondering, how did I do that? Or how am I going to do this quickly? Here's kind of a stepwise approach. Okay, and this is the problem that we just looked at. It's the exact same thing. I just solved it first. You're going to look at the hydrogen atoms and the methyl groups on the next door neighbors. Okay, so you just go to the next carbon over and just evaluate what's going to happen. Identify all the hydrogens, all the methyl groups. So there's the total 2 hydrogens here. Here there was a hydrogen. Here there's a methyl. And we even tested to see what would happen if we were to shift any of those. We didn't make anything more stable. However, you see that when you, I meant the methyl. But we saw that once you shift this hydrogen, you end up with something more stable. And that is something that you'll actually train your eye to be able to do much quicker. Like you won't have to draw it every single time if you practice. Now, are there any other type of rearrangements? The answer is yes, and there's other ones that aren't covered in our book, but there's one more that I want you to be aware of. A tertiary carbocation usually is not going to undergo a rearrangement. However, it can, okay? It can under a certain situation. If you go from a tertiary carbocation, it is going to rearrange if it forms one that is tertiary resonance stabilized. Okay, a tertiary carbocation that is resonance stabilized is more stable than one that is just a plain old regular everyday tertiary carbocation. So let's take a look at this guy over here, right? Here you have a beautiful tertiary carbocation. There's nothing wrong with that at all, but it will undergo a hydride shift in this case. So this is a 1,2 hydride shift. It is happening. Why is it happening? Because now you've produced something that is tertiary and it's resonance stabilized. Tertiary and resonance stabilized. So it's a double whammy. Okay? And that's the kind of thing, like, how would you recognize that? You train your eye to notice it, is really all there is. All right. So what's an allylic carbocation? An allylic carbocation is nothing more than a carbocation in which the positive charge is adjacent to a carbon-carbon double bond. So you've got, right, the positive charge, single, right? And how many allylic carbocations did we see in chapter 2? Too many to mention, right? When we were practicing our patterns for drawing resonance contributors. Okay. Well, the last section of chapter 6 is this one right here. This is another kind of funny section in a way. It's almost like, and you're going to be like, oh, Mr. Dion, you didn't say this before. Well, it's almost like sections 6.1 to 6.6 are kind of like part 1. So we'll say 6.6 to 6.1, or 6.6, that's like part 1. And then 6.7 to 6.11, that's kind of like part 2. And then 6.12 is all by itself, kind of. It's like part 3 of the chapter. The reason why is because this is a topic that has to be taught to all students who study organic chemistry. However, it varies as to where it's placed in textbooks. At least that's my experience. So it's the whole topic of reversible and irreversible reaction arrows and mechanisms. This is something that's going to come up all the time in the class. So let's just kind of cover it, and then you'll have an idea as to why sometimes, right, this is just a proton transfer that's occurring here. But here they're saying it's reversible. And then this is a nucleophilic attack, and this is a loss of leaving group. But they're saying that this is irreversible, right? So a reversible and an irreversible arrow. How do you know when to draw which one? Well, the whole idea, or the whole question as to whether something is reversible or irreversible, to answer that, you have to take into account both kinetics and thermodynamics. And that's why it's stuck here at the end of chapter 6. So here's, some rules that you can use. Okay, and I'll kind of try to summarize it at the end. When you're doing a nucleophilic attack, okay, if the nucleophile that you're using is also a good leaving group, right? If it's the conjugate base of a strong acid, the nucleophile is also going to be a good leaving group. And so in that case, you would draw reversible arrows, right? Water makes a good nucleophile when you have a carbocation, but water, it can also make a good leaving group. Why? Because it's the conjugate base of what? Hydronium, right? Which has a pKa that's equal to negative 1.7, or negative 2 is close enough. All right, so that's rule number one. So if the attacking nucleophile is a poor leaving group, then you draw an irreversible arrow. Why would this be an irreversible arrow? Because this is methide, CH3 minus. It's a carbanion. CH3 minus is the conjugate base of CH4, which is methane, which is a pKa that's equal to 50. Well, I'm here to tell you, friends, it doesn't get much more less acidic than that. So since it's the conjugate base of such a crummy acid, well, then it's going to be an irreversible arrow. So this reverse reaction is never going to occur, okay? So that uses, pKa's that we've already learned. So the loss of a leaving group is virtually always reversible, okay? Virtually. So this is, now we've switched arrows from nucleophilic attack to our LLG. LLG is pretty much always reversible, because think about it. If you have a leaving group, well, that means it should be the conjugate base of a strong acid. So usually an LLG is going to be a reversible reaction. The whole idea behind good and bad leaving groups is going to be covered in more detail in chapter 7. I just mentioned it to my students in this chapter that a good leaving group is the conjugate base of a strong acid. Why? Because you know what a conjugate base is and you know what a strong acid is by now, and it takes me one sentence and you know what a good leaving group is. All right, so weak bases are going to be good leaving groups. So weak bases are the conjugate bases of strong acids. Strong bases are the conjugate bases of weak acids, therefore they're poor leaving groups. So that's the summary of what I've been talking about for the past 10 minutes, or what I mentioned 10 minutes ago. Proton transfers, just always write a reversible arrow. Nothing more to it than that. Unless, the exception is if the difference in pKa units is 10 or more, then it's considered irreversible. So both of these are proton transfers, right? This is a proton transfer, and this is a proton transfer. Here, the difference in pKa is what? 2.3. So we draw a reversible arrow. Here, the difference in pKa is what? 34, so 34.3. So there you go. We draw an irreversible arrow. And carbocation rearrangements, irreversible, because you're making something that's so much more stable. So there's no driving force for it to go backwards. So that's that. And this is just kind of a, last slide. It's not an aside or anything, but if you think about it, if you're thinking about thermodynamics and you're comparing relative energies, that's great, but you've also got to think of Le Chatelier's principle, okay? What's Le Chatelier's principle? That when a system experiences a disturbance in concentration, temperature, or pressure, it's going to respond to restore a new equilibrium state. So, and if you're like, oh boy, what's going on here? Think about it. What's N2? N2 is nitrogen gas, right? You're breathing it in right now. Okay, everybody is. Nitrogen is the major component of air. Well, if nitrogen is a gas, right, and you do a reaction where you end up losing N2, where's the N2 going to go? Up into the atmosphere. It's not coming back, okay? So this is going to be super irreversible. It's just going to escape the reaction flask. You're going to see bubbles. The bubbles go into the atmosphere, and that's the end. There's no way this could be irreversible. So whenever you lose a gas, whenever a gas is a product, the reaction is guaranteed to be irreversible, whether it's nitrogen or carbon dioxide or, whatever, sulfur, dioxide or something. If you lose a gas, it's not coming back. So that's irreversible. I'm going to back up all the way to the beginning of this section and just say a couple things about it. Again, it's kind of like just thrown in here at the end, but you can see why they put it in here. And this is just one of those things that comes up time and time again over, in Organic Chemistry 1 and in Organic Chemistry 2. Out of this textbook, David Klein's textbook, there is only one chapter and section that I have memorized that I know, it's this point, this, and it's this section. It's the only section I have memorized. Section 6.12 deals with reversible and irreversible reaction arrows. The reason why I have it memorized is because so often it's happened to me that I've been teaching, just enjoying life and teaching something to my students, and they'll be like, "Hey, Mr. Dion, why are these reaction arrows reversible and these ones irreversible?" And I'll be like, "Go back to section 6.12. We did cover it in that section." It's not something that you probably think about every day because you have a lot of things on your mind when you're studying organic chemistry. But again, it's one of these things that, you might want to refer back to it here and there, even after you've completed quiz 6, because you're going to see reversible and irreversible arrows come up almost Avogadro's number of times in chapter 7, in chapter 8, chapter 9, chapter 10, and chapter 11, which would finish up the course.